Well, good afternoon and welcome back to Complex Variables. I hope that you are diligently watching these videos from front to back. I hope that you are calling me with questions. I know a number of you have been, if there's a part that you don't understand, but this is working out pretty well. I wish that I could see you face to face because I love seeing you face to face, but that's not possible right now, and hopefully it'll be possible sometime in the near future. For now, let's pray. Let's start talking about complex variables. Father, in the name of Jesus, we realize that you are in charge, regardless of all that's happening in the world, Father. We know that COVID-19 didn't take you by surprise, and we know, Father, that you love us, that you want to take care of us, and we trust in that. And Lord, now we trust you for the understanding that we need, for me to be clear in teaching, for students to be clear in understanding. And Father, I pray that this semester will end well for everyone in this class. And we thank you, God, in Jesus' name. Amen. Okay, you may remember last time, hasn't been that long ago, that we were in the process of proving another theorem. We had already proven the closed curve theorem, essentially that if you have a nice function, you have a closed curve, the integral of the function on that closed curve is zero. We now are going to use that to prove the theorem that we just started. We're headed toward the Cauchy integral formula, and in order to do that, we have to do some intermediate work. And we had done some of that intermediate work last time. We were proving this theorem, that if f is holomorphic on some simply connected region omega, and if a is any point in omega, then if I define this new function g of z to be f of z minus f of a over z minus a, provided that that's defined, that z is not equal to a, and if z is equal to a, I just make it the derivative, because you'll notice that this difference quotient, the limit of that as z goes to a, if that limit exists, is the derivative. So we're going to define this new function in terms of the difference quotient away from a and the derivative at a. And the punchline to this is, then g has an antiderivative. And you remember an antiderivative just means that its derivative is our original function g, that's true throughout omega. And then this equation star, our usual, the integral over gamma of g of z is equal to 0 for all gammas contained in omega, a simple closed, if gammas are simple closed curves. So that's the theorem. We want to prove star. And by the previous proofs, you recall what I mentioned last time, it's enough to show this integral is 0 for a rectangle, because then we generalized it and finally got it to piecewise smooth curves. And so case one, now we're doing this for a rectangle, but case one is if A is outside the rectangle. If A is outside the rectangle, then you can choose an omega so that A is outside of omega, which means that g is analytic there, because there's no problem of dividing by 0 if a is outside of that rectangle, therefore outside of this omega that you've chosen that includes the rectangle but excludes the point a. So if a is outside the rectangle, everything is cool. That integral is 0 just by the closed curve theorem. But now let's do case 2. Suppose that A lies on the boundary of the rectangle. You may remember, now we're calling our rectangle R. You remember that this notation is not, it looks like the notation for a partial derivative, but it doesn't have a denominator, so it can't be a derivative. but this dr with the curve D is the boundary of R. So if it's not in your notes yet, put it in there. The boundary of our rectangle. So if A is on the boundary of the rectangle, let's let epsilon be greater than 0. Okay, now what we're going to do is we're going to divide our rectangle into 6 rectangles. Now I know you have a bit of a glare on your screen, but hopefully you can see this because I want to keep this kind of out of the way. Here is my point A on the boundary of the rectangle. Okay. Now what I'm going to do is I'm going to divide this thing up. So I'm going to put one segment just above A, one segment just below A, and one segment just to the right of A. So now I've divided my original rectangle into 1, 2, 3, 4, 5, 6 rectangles. Okay? And this little rectangle here, I'm going to call R1. All right? Now, we get, if we're integrating along the boundary of the big one, then as we've done several times already before, you can integrate along these rectangles and all of the interior paths cancel. Because this one is canceled by this one, etc. So the inside paths cancel each other, and once again, the only one that counts is the boundary of the rectangle. And the only you remember that if A is outside a rectangle, since G is analytic, the integral is going to be 0. Now I didn't make this very clear. G is analytic on omega, and by the closed curve theorem, the integral is 0. The integral star equals 0. Sorry about that. I don't want to leave that out. That's very important. That's what we wanted to prove after all. Okay, so every one of the rectangles that does not have A on the boundary or A on the interior or anything else, all of those, the integrals are 0 by the closed curve theorem. So the only one that really matters is R1, the rectangle that has A on its little boundary. Okay, now, so we've chosen R1 so that the length of the boundary of R1 is less than epsilon. Well, that's easy to do because A is a single point, and notice that I took this upper bound to be just a little bit above A, the lower one to be a little bit below, because I wanted the length of all of R1, all the 4 little segments, the sum of those to be less than epsilon. Okay, so that's where we're at now. And note that G is continuous since f prime exists, so the limit of the difference quotient is f prime of a, and so g is a continuous function, since f prime at a exists, hence g is bounded. And that's on R1. Okay? It's bounded because I have a closed interval, and the function is continuous on that closed interval, so the function is bounded. A continuous function on a closed interval, on a closed rectangle, or any closed set that is bounded in the complex plane, that continuous function has a maximum. So it's bounded on R, say R1, say the absolute value of g of z is less than or equal to m on R1. Okay? Then let's do some arithmetic. The integral over the boundary of the big rectangle of g of z dz, as I mentioned before, that's the sum of the integrals over the 6 smaller rectangles because of the cancellation on the paths inside. So this is from, say, j equals 1, the sum from j equals 1 to 6 of and let's put this integral sign inside. So it's going to be the sum of these integrals. And this is g of z dz. But all of them, of course, are 0 because of the closed curve theorem, except for R1, which is equal to the integral over the boundary of R1 of g of z dz. But the absolute value of the integral over the boundary of R1 of g of z dz, as we've done many times before now, is less than or equal to the integral of the absolute value. D absolute value of z, which is less than or equal to, now absolute value of g of z is bounded by m, so times the integral over the boundary of d absolute value of z, but the length of this curve, this little rectangle, is less than epsilon. So this is less than m times epsilon, so the integral equals 0. Integral over the boundary of R of g of z dz is 0. And that takes care of the case when A actually lands on the boundary of R. The only case that's left, we had A outside the rectangle. We have A on the boundary of the rectangle. The only thing that remains is if A is in the interior of the rectangle. So case 3. If A is inside R. Okay, well, if that's the case, once again, let epsilon be greater than 0. And now we're going to divide R into 9 rectangles. Now, don't panic. It's not really very complicated. So here's the idea. In fact, I'm going to do this. No, I'm going to do it right here. So you can't see it yet because I'm a better door than I am a window, but here's A. It's in the interior of the big rectangle. And what I'm going to do is I'm going to surround A once again so that it's inside a little bitty rectangle. So I'm going to put one segment just a little bit to the left, another segment a little bit to the right, another segment a little above, and another segment a little below. And so now I have 1, 2, 3, 4, 5, 6, 7, 8, 9 rectangles. A is inside one little rectangle. And you can imagine we're going to do the same thing. All of the interior paths cancel, their integrals cancel. So the only thing that counts is the integral on the outsides. So here the integral over the boundary of the big rectangle of g of z dz is equal to the sum from j equals 1 to 9 of all the integrals over the boundary of the subrectangles g of z dz. But for 8 of the 9 rectangles, those integrals are 0 because of the closed curve theorem again. So the only one that really counts is this small one. And once again, we're gonna call that rectangle R1. So the only one that counts is the integral over the boundary of R1 of g of z dz. And if we chose R1 so that the length of its boundary is less than epsilon, and the absolute value of g of z is less than or equal to m on R1, we again get that the integral is equal to 0. And that is the end of the proof. And it's good that that's the end of the proof. Otherwise, I would have had to start writing on the wall and nobody would have appreciated that. So that takes care of this theorem. The next theorem that I want to prove is called Cauchy's integral theorem. Actually, Cauchy's integral formula. We're going to have several theorems coming up now that are absolutely marvelous in their strength. And hopefully you get a chance to share with me the awe of these things. But first you get to share with me the erasing of the boards. I'd say talk amongst yourselves, but there probably are not very many of you together. So that wouldn't be very entertaining. This is where you get potato chips and dip. But don't take time to fix yourself lasagna because you'll miss the next part of the lecture. Unless, of course, you pause the YouTube. Then by the time the lasagna is fixed, you're going to forget what we were talking about. So it's best to just wait. Okay. Thank you for waiting. Now, Cauchy's integral formula, there are actually two Cauchy's integral formulas that we're going to do. The first one is certainly the simpler of the two. The second one we're not going to prove, but the proof is in your textbook, so if you want to look it up in the Sean's outline, feel free. But Cauchy's integral formula, which I'm going to call Cauchy integral formula 1. The usual setup. If f is holomorphic on omega, a simply connected region, A is some point in that region, and gamma is a simple closed curve inside that region. Then f of A is equal to 1 over 2 pi I integral over gamma of f of z over z minus a dz. Now, before we prove this, I want to just point out the immense power of this statement. If I wanted to integrate anything that looks like f of z over z minus a, and if the numerator is a holomorphic function, now obviously the whole thing is not holomorphic at a because you've got z minus a in the denominator, but if the numerator is holomorphic and I want to integrate f of z over z minus a, then all I have to know is the function value at one point in omega, and that tells me what the integral is, because the integral will be 2 pi I times f of that point. It's absolutely a miraculous theorem. And so it'll be a miracle if we prove it too. No, it's not that hard to prove. Proof. As before, let's define a little g. So g of z is equal to what it was equal to before, f of z minus f of a over z minus a, if z is not a, and the derivative at a if it is, if z is a. Okay? So by the previous theorem, zero is the integral over gamma of g of z dz. Okay, so that's our starting point. And why? Because g is holomorphic in omega, and this isn't very clear here. And so we got that the integral was equal to 0. Therefore, now let's do some arithmetic. 0 is equal to the integral. Now we're going to use these formulas. The integral over gamma of f of z. We're going to split it up. F of z over z minus a dz minus the integral of f evaluated at that point divided by z minus a. And since 0 is equal to that difference, then those two integrals are equal. So the integral of f of z over z minus a with respect to z, that integral over gamma, is equal to the integral of just this constant value, f of a, over z minus a with respect to z. Okay? Now here's what we're going to do. We're going to split gamma up into two curves. So here is gamma 1, and we're going to split it up right here. And here is gamma 2. And everything is still oriented positively, which means counterclockwise. Now what we're going to do, I'll use a different color, which I hope comes through on the video. But we've got A right here. And we're going to put a line segment from A down to the curve and another line segment from A up to the curve, and but not all the way, not all the way from A. We're going to put a little circle around A. Okay? And this, the left side of that circle, we're going to call small case gamma 1, and that's going to be oriented in the direction upward. And on the right-hand side is going to be small case gamma 2, which is going to be oriented downward. And both of the line segments are oriented upward. Okay? This line segment is going to be L1, and this line segment is going to be L2. Okay? So that's the situation. And of course, our curve gamma is equal to gamma 1 union gamma 2. So let's see where this thing goes. By the closed curve theorem, let's see, I need to protect your eyes from that glare, I guess. But by the closed curve theorem, 0 is the integral over gamma 1 dz over z minus a plus the integral over L1. I'll show you from the picture. Let me write down the equation first of the same thing, plus the integral over gamma, little gamma 1 of the same function, plus the integral over L2 of dz over z minus a. Now, why is that? because that's a simple closed curve. If I go along gamma 1, and then I go up L1, and then I go around to the left on little gamma 1, and then I go up L2, it closes right here, and that integral therefore is 0 by the closed curve theorem. Okay. But let's do one of these integrals. The integral over gamma 1, say. This is a little circle around A. So whatever is the radius of that circle, if the radius of the circle made up of gamma 1 and gamma 2, little gamma 1 and little gamma 2, if that radius is r, then this is going to be the integral dz over z minus a over little gamma 1 is going to equal the integral from 3 pi over 2 up to pi over 2 of, now the denominator, this is going to be r e to the it, and then the numerator is r times I times e to the it, because you take the derivative, times dt, which is equal to minus pi times I. Okay? So that integral is the same as if a were 0 and this were just a small circle around 0. The value of the integral is going to be the same. And so evaluating this integral from 3 pi over 2, which is down at the bottom of the little circle, to pi over 2, which is up at the top of the little circle, is I times negative pi. Okay? So we've got that one. Therefore, now I'm rearranging this thing that's equal to 0, but this particular integral being negative pi I, therefore, the integral over gamma 1 of dz over z minus a. By the way, this is a sneaky trick that you actually use a number of times in complex variables, and so you're learning a new sneaky trick. That's equal to, now, this integral over little L1 plus this integral over little L2 is really the integral of this over the union of those two lines. So we'll combine those together. And because they're on the other side of the equation, that's going to be minus the integral of dz over z minus a over L1 union L2, little L1 union little L2. And then, of course, plus, this went to the other side of the equation too, so plus pi times I. Okay. Similarly, on the right-hand side with this closed curve involving big gamma 2 and then going down L2 to the right, little gamma 2, and down L1, similarly this integral over big gamma 2 of dz over z minus a is equal to, in this case, plus, because now we've changed the orientation of the two line segments, So over gamma 1 union gamma 2, the little ones, small case gamma 1 union small case gamma 2 of the same thing over Z minus A. But also plus pi I for the same reason that it was before. Okay? So now we've got this equation and this equation. So now let's do our arithmetic. Therefore, the integral over the big curve all the way around of dz over z minus a is equal to the integral over gamma 1 of dz over z minus a plus the integral of the same thing, dz over z minus a over big gamma 2. And the only thing that doesn't cancel is pi I plus pi I. So this is 2 pi I. Hence, the integral of f of z over z minus a dz is equal to f of a times 2 pi I, which is exactly what I wanted to prove. Okay, so and that, by the way, is from here. So that takes care of Cauchy integral formula. Amazing, as I said before, an amazing theorem, because if I want to know the integral over some simple closed curve of some function that's holomorphic over z minus a, that integral is 2 pi I times the function value at that one point at a. Absolutely a miraculous thing to notate. Cauchy was indeed a genius. Now, let's take a look at an example that has been puzzling so far all semester and see if we can settle an issue once and for all. And the issue is this. What is the integral of 1 over z with respect to z over the unit circle? Well, by Cauchy's integral formula, it's the function value of the numerator, which is 1, times 2 pi I. Pretty simple answer. Let's suppose that I use the antiderivative theorem. Well, then the integral of 1 over z dz over the unit circle is equal to the integral of the derivative of the natural log over there. But of course, the unit circle goes from 0 to 2 pi, and the log is equal at those two endpoints, so wouldn't that be 0? Now, how do I define which one is the correct answer? And then there's another way to do the integral. On the unit circle, z of t can be written as e to the it. So the integral over the unit circle of 1 over z dz is the integral from 0 to 2 pi. That doesn't look like a 2. 0 to 2 pi of 1 over e to the it times the derivative I e to the it times dt, which is equal to, there's cancellation of the e to the it's, I'm left with an I on top. I evaluate it from 0 to 2 pi, so I get 2 pi minus 0, which is 2 pi. And so again, the answer is 2 pi I. So it looks like the votes are in favor of 2 pi I rather than 0. So my question now is, well, what's wrong with the middle one? And the answer is, the natural log of z is not even defined over all of that unit circle. Because once you go around once, for the log of z, you end up on a higher Riemann surface. And that function's not even continuous there. So holomorphic is way out of the question, let alone, so differential being holomorphic, that's out of the question. So the middle one just isn't correct. The answer is 2 pi I. So Cauchy's integral formula will help us settle a lot of issues. Let's do a couple more examples. But first, a word from our eraser. Holding a pen while you're erasing is kind of counterproductive. Okay. So some examples. Let's do one that looks really ugly. The integral over gamma of 3z squared plus z minus pi all divided by z minus a dz, where gamma is a simple closed curve as usual, with a inside gamma. Okay? And what is that integral? I always told calculus students that my favorite problems were the ones where the first step was to write down the answer. Take a look at the numerator, 3z squared plus z minus pi. That function is a polynomial. It's holomorphic everywhere. It's entire. Divided by z minus a, and so by Cauchy integral formula, So the answer by CIF, Cauchy integral formula, is the top evaluated at A, so 3a squared plus a minus pi, all times 2 pi I. And that is the end of the problem. So before you start trying to divide and do all of that weird stuff, just remember the Cauchy integral formula gives you the final answer immediately. Okay? Let's do another one. How about the integral over the circle around 2 of radius 5 of z squared plus z minus 1 squared, z squared, z cubed, all divided by z times z minus 1 with respect to z. Well, now if I'm really clever about this, I'll divide the numerator up into the two parts and integrate them separately. This is the integral over the circle of radius 5 around the point 2. So here's what's happening, by the way. Here's my complex plane. Here is 0, here's 1, here's 2, and the circle of radius 5 around 2 encloses everything. All right? Now, let's take z squared over the denominator and integrate that first. And then let's take the right-hand side, z minus 1 squared times z cubed, over the denominator and integrate that second. With respect to z. Okay? Now, what happens here? I can cancel a z. So this is the integral over that same circle of z on top and z minus 1, because the other z turned into a pumpkin, plus integral over that same circle and a z minus 1 cancels, and a z cancels. So here I'm left with a z minus 1 on top, a z squared on top, dz, and nothing on the bottom. Okay? So, now what do I do? Which of those integrals is just absolutely trivial? The one on the left or the one on the right? If you said the one on the right is absolutely trivial, you're absolutely, pardon the pun, right. Because this function is totally holomorphic. It's entire on the on the complex plane. So this integral is 0 by the closed curve theorem. So what about the one on the left? Well, the one on the left is the top evaluated at this point. This is my A. So A is 1. So Z evaluated at 1 is 1. So that's 1 times 2 pi I, that's Cauchy's integral formula. The other one is 0. So the answer is 2 pi I. Okay? This other one has nothing to do with Cauchy's integral formula, so I won't bother with that one. So hopefully some of this stuff is starting to become, it won't be second nature yet, but it will be sometime soon. So hang in there. And now, time to do two things. To erase the boards and to get a drink of iced tea. I would imagine that it's tough to remain diligent and taking notes and all of that when you're really just kind of watching TV on your computer screen, or maybe you have uploaded it to your television. But make sure that you don't blow it off. You know, this is not the Dick Van Dyke Show. This is still something worth taking notes on. Part 2, my drink of iced tea. Okay. Next. You've noticed that on all of these theorems, gamma was a simple curve. What if it's not? Suppose that gamma goes round and round and round and keeps intersecting itself. So if gamma is not simple, then what? What we're going to get then is if it wraps around k times we'll get 2 pi k times I is the integral of dz over z minus a, which is equal to, as we've done many times already, the integral from, say, c to d of z prime of t dt on top, and z of t minus a on the bottom, where gamma is defined by z of t, where t is in the interval from c to d. Okay? Let's prove this. This is proof by sneaky trick. Define a new function, phi of s. And phi of s is going to be e to the power of the integral from c to s, so that's where the variable will be, of z prime of t dt over z of t minus a. Okay? So question. What's phi prime of s? Well, that's pretty easy. What's the derivative of e to the garbage? The answer is e to the garbage, which is phi of s, times the derivative of the garbage, but the derivative of the integral is going to be the inside function evaluated up here. So that's going to be z prime of s over z of s minus a. Okay? Therefore, and I'm going to call this next equation star, if I move everything to the same side, I'm going to get z of s minus A, that quantity. So I'm just clearing the denominator and moving everything over. So times phi prime of S. First of all, I don't even have to move everything over. That's equal to phi of S times z prime of S. Okay, so I'm not going to move it over. I'm just going to leave it where it is, but I'm going to multiply both sides by the denominator. Okay, but what is the derivative? Now another sneaky trick. What's the derivative of phi of S over z of S minus A? Okay, let's differentiate this thing now. Well, this is baby calculus. This is the derivative of the top times the bottom. Minus the top times the derivative of the bottom, z prime of S, divided by the bottom squared. But phi prime of S, z of S minus A equals phi of S, z prime of S. So when I subtract them, I get 0. So the derivative of this thing is equal to 0. What kind of a function is it if its derivative is 0? And the answer is, it's a constant function. So therefore, phi of S over z of S minus A equals a constant. Okay? Now, I wonder what the constant is. No, I don't. I know what the constant is. What is the constant? Well, since it's a constant, then it would be a constant no matter what number in the interval from 0 to d I plug in. So let S equal the left endpoint, C. So I get phi of S over z of S minus A is now equal to phi of C over S of C minus A. But what's phi of C? Well, the variable gets plugged in up here. So this is the integral from C to C. And from C to C, this integral is 0, and e to the 0 is 1. So this is 1 divided by z of C minus A. So that is my constant. All right. Hence, I don't use the word hence nearly enough. Phi of t is z of t minus A over z of C minus A, because if I take, where is it? If I take this, phi of S, and I just plug in t for S now, phi of t is equal to our constant, which is this, times z of t minus A, I get this. And since the curve is closed, What's phi of d? Well, phi of d is equal to z of d minus a over z of c minus a. But because the curve is closed, z of d equals z of c, so this is equal to 1. Therefore, e to the stuff equals 1. So what do you, right? That was our integral. E to the stuff equals 1. So what does the stuff have to be? It has to be 0. So the stuff equals 0, or if I wrap around again, 2 pi I, if I wrap around again, 2 pi ki in general. So 2 pi ki, which is to say the integral of dz over z minus a over gamma is 2 pi ki, where k is called the winding number. The number of times the curve winds around A. Okay. So now I want to prove, let's see if I have enough time to prove this. Sure, it's easy. The fundamental theorem of complex analysis. Does that sound important or what? Okay, we're going to prove that. But first I want to, let's see, do I want to state something? Yeah. So this is a by the way. Cauchy, I mentioned that there were two of them. Cauchy integral formula 2 has to do not just with the function value at A, but with the values of the derivatives at A. So it goes like this. The nth derivative of the function at A is equal to n factorial over 2 pi I times the integral of the function f of z dz divided by z minus a to the n plus 1 power. Okay, where n equals 0, 1, 2, blah, blah, blah. And recall, the 0th derivative of a function is the function. So as a special case of Cauchy integral formula 2, when n is equal to 0, you get Cauchy integral formula 1. All right? But this one now is much more general. It's true for all the derivatives. Okay. So let's see if we can squeeze one more proof into here. I'm having a good time proving this stuff. I hope you're having a good time watching this stuff. And for heaven's sakes, don't text during the lecture. That's terrible in class, and it's terrible during these video lectures. So, don't be checking your Facebook page. All of that's just really terrible manners anyway in a class. So, all right, sermonette is over. The fundamental theorem of complex analysis. Fundamental theorem of complex analysis. And it goes like this. I'll bet you can guess a lot of this. If F is holomorphic in a region, then for all A, all points in that region, the kth derivative exists for all K, and the function itself is a power series. So it's the sum from k equals 0 to infinity of the kth derivative evaluated at a times z minus a to the k divided by k factorial on z minus a less than r, say, where r is the largest radius of a disk around A that is still contained in omega. Okay, so that's what I want to prove next. And to do that, we're going to prove a lemma. So, a lemma. If the absolute value of little w is equal to r, the absolute value of z is less than or equal to the absolute value of some fixed value of z, z sub 0, where z sub 0 lives in the disk of radius r around A, I'm sorry, around 0. Let's do this at 0. Then I have a formula for 1 divided by w minus z. And it turns out to be the following series. 1 over w plus z over w squared plus z squared over w cubed plus blah, 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 which converges uniformly on that boundary. Okay. And let's prove that. Okay, so here we go. As soon as I get these pages pointing in the right direction. Okay. So first of all, using the Weierstrass M test, these are S's, which we've talked about before and which you hopefully got in advanced calculus or Calc 3. Applied to, what are we going to apply the M test to? Z over W in absolute value to the K. Now, here's how we're going to do this. If we choose some R sub 0, which is less than, strictly less than capital R, and let little r equal the quotient R0 over R, big R, then R lives in the open unit interval, little r. Okay. Now suppose that Z0 lives in the disk around 0 of radius big R0. Therefore, absolute value of Z0 divided by big R is less than 1. I'm sorry, less than little r. So, absolute value of Z0, absolute value of Z, any Z in fact, Z over W to the K is less than little r to the K. Therefore, the sum of Z sub K is less than the sum of R to the K, which is finite. We're going to have to end there because it's about time for class to be over, and there's a little bit of arithmetic left. Now, very little arithmetic. In fact, the sum of R to the K is equal to 1 over 1 minus R. So, the sum of Z over W to the K without the absolute value converges uniformly to 1 over 1 minus Z over W. But one last line here, might be 2 lines. I'll try to do it in 1 line. 1 over W minus Z is equal to 1 over W, factoring out a W even though you can't. Pull out a 1 over W, and what am I left with? 1 over 1 minus Z over W. This is equal to 1 over W times the infinite series from K equals 0 to infinity of Z over W to the K, which I'm going to write as 1 over W plus Z over W squared plus Z squared over W cubed plus blah, 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 which is exactly what we had to prove for the lemma. So we will start next time with the rest of the proof. Thank you for coming to class today, and God bless you and keep you all safe. We'll hear from each other on Monday. So long.